In this video, we're going to move on from our study of the kernel of a linear transform and introduce a new idea called the image. Now, an important idea of where this is going, which can help put all this in context, is that if we have a linear map from one space to another, we can talk about the dimensionality of that input space. And you can think of that idea as we have n dimensions to play with. What happens to them as we go through this transformation? It's going to turn out we're going to prove that these n dimensions are going to get split into two aspects. Some dimensions are going to be associated with the kernel of L, all the values from the input space, part of these n dimensions, that get mapped to the zero vector, and the rest of them are going to be somehow represented by the output of that transformation. And we're going to call that set of points the image. Let's define that image a little more carefully. Imagine we have our transform. So again, we have an input space V, an output space W, and a linear transform that maps points in one to the other. If we now imagine all the points in V and where they end up in W, well, they might not cover all of W, but they might have some representative subset of that. This collection here is what we're going to call the image of L. And notice in contrast from the kernel is a subspace of the input space. The image is more naturally what we think about in calculus as range. It's the subset of the output space that we can reach with our transformation L. As a quick side note of nomenclature, image of L is a set of reachable points in W through our transform L. The W itself, the entire set, is called the codomain, the target set, or sometimes the output set. And so clearly the image is a subset of that bigger set. It might be equal to, it might just be a single point, but everything in the image is in W because that's where the output of our transform lands us. So just to reiterate that, the kernel is some part of the input space that maps to the zero. That kernel is equal to a set of V's from the input space. How does it involve the linear transform? Well, it's all the V's that map to the zero vector in the output space. The image is a subset of the output space. So what is it? It's a bunch of W's in the big W set such that there exists some input V that when I transform V, I can actually reach that W vector. So there has to be some, if you like, inverted point V that I can get back to from the output space. And that image may or may not be all of W. Sometimes it is, sometimes it isn't, and that's one of the things we're going to explore. So let's just tease this out with something a bit more concrete. Let's imagine we have the plane XY mapping to the 3D space R3 and see what we get with that. And we're going to study this through a series of points. And we'll start off with the 0, 0 point. And when we plug 0 in for X and Y here, we're going to get 0, 0, 0, 0. Well, that is the zero vector in R3. And so this point maps to the origin over here. And we actually knew that because L is a linear transform. Therefore, the zero vector always maps to the zero vector in the output space. Now, if we take the point 1, 0 and figure out where it maps to, it's going to give us 1, 0, 1. And so that's 1, 0 in Y, 1 in Z. So there we are. And let's do another point at 0, 1. When we run that through the transform, we get 0, 1, 1. And that is 0 in X, 1 in Y, 1 in Z. And let's do one more. Let's do 2, 0 here. So L of 2, 0 is going to be 2, 0, 2. And that would actually be 2 and 2. Okay, so that's in a line along here. You imagine a line along here. With the linearity, it probably doesn't come as a huge surprise that we're talking about some kind of plane in 3D here. Get these lined up. So a plane through the origin. The image of L is equal to a plane through the origin. We would like to back that up, don't get me wrong, but as a quick sketch, that seems reasonable. Let's try a different transform. Let's go down here and look at G of XY. And we'll do the same thing. We're going to take the 0, 0 point and find G. Sorry, these should all be F's, I apologize. That should be F, and F, and F, and F. All right, so now G of 0, 0, again, if this is a linear transform, and it is, g of 0, 0 will be 0, 0, 0, and in fact that's what we get. So it maps the same way. Let's then compute g of 1, 0, and that is 0, x minus y is 1, and y minus x is negative 1. So the point here at 1, 0 maps to 0, 1, minus 1, so down here. Now let's do g of 0, 1. So pick a point up here. G of 0, 1 is again 0, and x minus y minus 1, and y minus that is positive 1. And just to round it off, let's try a point here at 1, 1. G of 1, 1. And that's going to be 0, and 0, and 0, 0, 0. Ah, well that's interesting here. That actually maps to the origin as well over here. And I realized I forgot to draw this point here. 0, minus 1, plus 1. That's up here. Oh. Well, that's interesting. It feels like this time all the points in our output are lining up along a line. Again, we'd like to prove that, but at a quick check, and you can plug in some more values, they seem to end up along this line here. And so the image of L is equal to a line through the origin for this particular transform. Again, it's all contingent on the function that we're actually using through the origin. And there's also a subtle thing that's popping up about the kernel over here. If we think about the kernel, what's the kernel? The kernel is all the points over here that map to the 0 vector. Again, we don't have proof, but the only point that we found was the 0, 0 point. So here, the kernel of the function f here was just a set, and it was just the 0, 0 point. That's it, single point. And if you like, another way to phrase that is it's a 0 dimension. It's a 0 dimensional space. The only thing that maps to 0 on the output is just the point 0, 0. Whereas this is a plane which is 2D. Over here, again, we had 2 dimensions to start with, but the kernel of the kernel of G here, kernel of G, well, both the blue dot and the black dot here map to 0, and wait, we had a theorem earlier that said it's not just going to be those points, it's going to be a subspace related to that, because the kernel is a vector subspace, which means any scalar multiple of those will also map to the 0 vector. And so the kernel of G is also equal to a line in R2, and that is one-dimensional. Meanwhile here, this line over here is also one-dimensional. We started with 2 dimensions, and if we start with 2 dimensions, we can get a plane, which is 2-dimensional, or it seems like we can start with 2 dimensions and get a line out. Well, where did the other dimension go? It feels like the kernel is sort of representing a collapsed version of it, because everything along this line here maps to the 0, 0 vector. Sorry, the 0, 0, 0 vector in R3, in our output space. So everything along here, in some sense, gets collapsed to the 0 point. The informal way I think about that is a dimension got collapsed, and so there's only 1 dimension left from our 2 dimensions that we started with. Let's see if we can drag that out to a more extreme example, where our transform is simply whatever x and y are, I get the 0, 0, 0 point. So here, if we have h of 0, 0, well, we're going to get 0, 0, 0. If I have h of 1, 0, I'm going to get, 0, 0, 0. In fact, every point on here maps to the 0 vector on the output space. And so the image of this function h here is simply the point 0, 0. That's it. Meanwhile, what inputs map to the 0, 0? Well, everything here. The kernel of h is equal to any x and y that's in R2. So that's a 2D space, and it maps to a 0D space, a single point in the image. So we start to see this teaser that when I start with 2 dimensions in the input, a pretty common thing to have happen with most linear transforms is we're going to get a 2D space back out. It might be embedded inside a larger space, and that's fine. But if it turns out that I start with 2D and I only get a 1D space back, well, the kernel is going to start to get more interesting then. And likewise, if we have a 2D space and we map to 0 dimensions, so we squish this whole thing down, that's going to be reflected in the kernel as well. So that's going to give us some ideas for how to work forward with kernel and image and how they relate to linear transforms.